phase plane is one way of looking at a system response. It's really only valid for a second order system, but it kind of gives some insight into a lot of the things that are going on. So consider for now a second order unforced system. x1 dot and x2 dot are functions of x1 and x2 with their initial conditions. This side of the equation expresses something called the tangent of the solution, where x1 and x2 are the state solutions. So for a second order system, we have two states, and so we can plot the response x2 versus x1. The vector field can also be plotted on the same axis. So the vector field is actually associated with these functions. Notice that these functions are functions of x1 and x2. And we can plot them this way. So the vector field here is such that the vectors, so notice that these vectors have length. Sometimes the vectors are really small in length. But so they have two things. They have direction and they have length. So the slope can be shown to be given by this expression for any of these guys. Okay, and so this is this. So again, this is x1, this is x2, and I'm basically plotting the solution of these. Actually, I'm plotting these functions as a function of x1 and x2. And what these arrows show is that they show the trajectory of the system at that point. So for example here, if I have a state here, notice I have no input. So my system is responding just to the initial condition. If my system is at this point, it's going to head, the system response will head in this direction. Okay, if it's here, it'll head in this direction. If it's here, it'll head in this direction. So you can see it's heading into the origin, and it's kind of doing it in a particular way. Okay, so here is what's called a Comet plot that shows an example, a set of example responses for this system. So if I start in these various locations, it shows me what happens to the response. Okay, so I basically started in 4 different places, and it has shown me the response in each of those different situations. And you can see how the actual response of the system, given the initial condition, follows the vector field. And again, the vector field is basically these functions plotted at each x1 and x2. We plot the arrow that is associated with this, and so we can actually use the vector field to show us the basics of the response of the system. And so for a second order system, we get particular responses that occur as a result of how the different eigenvalues of the system are situated. Now in this case, I actually have a nonlinear system. I can do it for a nonlinear system, or I can do it for a linear system. So now we're going to look at a number of linear systems and their eigenvalues and see how the poles affect the overall response of the system. So here's the system, 2 poles, one at -2, one at -1. It's diagonal, and so each of these shows the response of the system. They're all heading into the origin. Okay. And so we can see what's going on. Notice that in general, things tend to head in before heading in the x direction before heading in the y direction. And that's because the eigenvalue from x1 is larger, or rather further to the left, than the eigenvalue for x2. That means the convergence in the x direction, the x1 direction, is faster than the convergence in the x2 direction. And so that's why we get this kind of response. Things are heading in faster than they're heading. So notice at this point, it's heading both this direction and that direction, but it's just heading faster in this direction than it is in that direction, and so forth. Notice that if we start on an eigenvector, so notice this is actually an eigenvector for the system. So remember whenever we have a diagonal matrix, the eigenvectors are the unit basis vectors. So or the basis vector. So In this case, if I start on this line, I stay on this line all the way in. If I start on this line, I stay on this line all the way in. Okay, so that's we can see some important things as a result of this. So this is the case when I have two eigenvalues, and they are distinct eigenvalues. Now I have a Jordan form, and I have two eigenvalues, both at -1. It's kind of hard to plot them exactly at -1. And we can still see that the system is heading into the origin. And for example, here, if I start on this eigenvector, it's going to take me into the origin. But notice that there isn't another vector like that. Okay, and that's because this matrix is in a Jordan form. As a Jordan form, it only has one eigenvector. Okay, it has a generalized eigenvector, but it does not have another eigenvector. So there's only one vector like this for this particular system. Otherwise, if we start here, it zooms into the origin, but it zooms in at a kind of a skewed way. Here we have a system, and in this case we have two poles that are complex. And you can see it kind of spirals into the origin depending on where you start. It goes to the origin, but it spirals in. All right, so now we have the poles are located at this place. If we shift them further to the left, we can see that basically I get a faster convergence. That is, it has less time to spiral as compared to this one. So this one has more time to spiral because the convergence is slower. Here the convergence is faster, and so it doesn't spiral as much. Okay, so notice that in this case, the difference between these two matrices is these values, and notice that these values basically whenever I have a matrix that looks like this, it actually has the diagonal elements are the real parts of the complex eigenvalues, and the off diagonals are the frequency, that's the imaginary component. So here, notice that the real part is faster than the imaginary part. What happens if we have it the other way around? What happens if the imaginary part is faster than the real part? So like this. Well, that means it converges, but it converges slowly, and since the frequency is fast, it's able to spiral more as it goes in. Okay, so we get a more oscillatory response in that case. Here we have the two poles like we had in the first case, but notice that they're not it's not a diagonal matrix. And so we have the whole thing skewed. Notice now our eigenvector is actually, one of the eigenvectors is along this line here. There is actually another eigenvector. I'm not sure how to see it. I think this may actually be the other eigenvector here. It's very close to that. So this is the response. We have a different set of eigenvectors now. Here's what happens if we take those eigenvalues and we shift them here, and we have it still in this form. We get spiraling in a kind of skewed and squashed way. Here now we have one eigenvalue at the origin and the other eigenvalue over here, and this is the kind of response we get. Notice that it does not go to it doesn't settle to the origin like the other cases. So it continues, but it doesn't stop at the origin. And so and the response from this guy, for example, never goes towards the origin. So clearly this system is unstable. It's not stable because it doesn't go to the origin. So this is so we have a pole on the imaginary axis, which is the boundary of stability. Similarly, here I have two poles at the origin, and this is the kind of response we get. It just continues on constant. So poles at the origin are definitely not stable. So we can talk about other terms and definitions. We'll come back next, and we'll look at some of these stability terms and definitions so that we can get a clearer grasp, a language for how to talk about stability.